Okay, so I am back. I took a little bit of I don't want to say call it a break. Life just kind of got in the way, and I wasn't able to do things. Um, but I'm back. We're at day 9, and man, do I have stuff ready for us. Okay, so one, we are definitely going to be doing day 9, the switch interfaces. Okay, we are also going to be doing the packet tracer from Jeremy's Tech Lab, and then we're going to do some practice IPv4 subnetting, okay, which is going to be really cool because I also have, where'd it go? Where'd Photoshop go? I also have this, which is, which is crazy dope, okay? I made this. No, I just want to, come on, just zoom in, damn it. There we go. So I made this little worksheet, chart, cheat sheet thing in order to help me better understand and always do the process correctly when finding subnetting. We'll go over this and how it works and why I made it. After Jeremy's Tech Lab, we've done the Anki cards, and we've done the packet tracer. So we are in it, okay? I'm also looking at making another day, 1 or 2 more days a week to study. I just don't know which one it's going to be. It's probably going to be Sunday, honestly. But we'll figure that out, okay? All right, let's hide that. Let's get back here. So this is what we're doing. If you're not subscribed to Jeremy's Tech Lab, you definitely should be. He has amazing videos, just absolutely amazing. Should definitely give them a watch. They're really, really good. We're going to watch this at playback speed, probably 1.5, maybe 1.25, maybe 1.5. Okay. And dang it, I forgot my water. Give me 1 second. I'm going to grab my water, and then we're going to get started, okay? 1 second. Hold on. We're good. Okay. So let's give it a watch, a gander, a listen.
If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. Also, remember
always, if anything else, like if you can't hear something or something's not whatever, just put it in the chat. Let me know.
To download and use the Anki flashcards with the link in the description, which will help you very much in remembering what you've learned. Let's get started. In this video, we'll take a break from IP addresses and take a look at switch interfaces. When we configured IP addresses, I talked about router interfaces a little bit. For example, we used the show IP interface brief command to check the layer 1 and layer 2 status of the interfaces. I also talked about how router interfaces are disabled with a shutdown command by default.
Yes, I remember.
This time we'll take a look at switch interfaces and see how they are different from router interfaces, and also how they are the same. Specifically, we're going to talk about configuring layer 1 characteristics of these interfaces, such as speed and duplex.
Hey, man.
So let me introduce what we'll cover in this video.
Hey, what's up, man?
I'll talk about interface speed and duplex. Speed refers to the data rate in bits per second, such as 10, 100, or 1000 megabits per second. Duplex is something I mentioned briefly in a previous video. Basically, it refers to whether a device is able to both...
Nice, good for you, dude. Did you pass on the first try? Or how many tries did it take you? That's really awesome.
Send and receive data at the same time. I'll talk about speed and duplex auto-negotiation, which allows two devices to negotiate speed and duplex settings without us having to manually configure them. I'll talk about interface status. I already talked about this in the previous video on configuring router interfaces, but I'll expand upon the topic. Finally, I'll talk about interface counters and errors.
Yes, first try.
Cisco devices keep various counters regarding the traffic that passes through them, such as how many errors have occurred, etc.
Dude, that's so awesome.
I'll show you how to find and analyze these statistics, and what kind of errors there are. Also, let me review one point about switches that I mentioned in the very first video in this series. Up top is a photo of a Cisco ASR 1000X router, and under it is a Cisco Catalyst 9200 switch. What's the big difference that stands out here? How about the number of interfaces? The router has 8 SFP interfaces for fiber optic cables, and then a few RJ45 interfaces for the console port and such. The switch, on the other hand, has 4 SFP interfaces, plus 48 RJ45 interfaces. This is because switches are used to connect and host to. This Catalyst switch might have 48 PCs connected to the RJ45 ports, and then connect to a router with the SFP fiber optic ports. Next, let me introduce the network topology I'll use for this video.
Nice,
this is a single LAN, 192.168.1.0/24, with one router, R1, 2 switches, switch 1 and switch 2, and 4 PCs, PC 1, 2, 3, and 4. In a real network with 2 switches, there would be many more end hosts, but just for this demonstration, I've attached just these 4 PCs. Switch 1 is the device we're going to focus on today, configuring its network interfaces including F01, F02, F03, and F04, which are connected, as well as the remaining interfaces, which are not connected at the moment. Let's go right into the CLI of switch 1. First, I use enable to enter privileged exec mode. After entering privileged exec mode, I entered the show IP interface brief command using shortcuts. As you can see, the 4 interfaces which are connected to devices, fast Ethernet 01, 02, 03, and 04, have a status column, which is the layer 1 status, and a protocol column, which is the layer 2 status, of up and up. We usually call this up. Keep in mind, I haven't done any configuration on switch 1 yet, except the hostname. So already, we can see a difference between Cisco routers and switches. What is that? Well, I mentioned briefly in the Day 8 video. Router interfaces are in an administratively disabled state by default, meaning they have the shutdown command applied.
Yes.
Switch interfaces, however, are different. They don't have the shutdown command applied. So if you connect them to another device, they'll usually be in the up state with no configuration required. Now, the IP address is unassigned, and it will remain that way because these are layer 2 switch ports. They don't need an IP address. The concept of multi-layer switching, where you actually do assign IP addresses to switches, will be for a future lesson. For this lesson, don't worry about the IP address column. Now, take a look at the other interfaces. Keep in mind I'm ignoring the VLAN 1 virtual interface. That will be a topic for another video. These other interfaces aren't connected to any other devices, so their status is down, down. Keep in mind, down and down is different than administratively down and down. Here's the show IP interface brief command on a router. Notice administratively down and down. This is because of the shutdown command. Down, down doesn't mean the interfaces are shut down. It means they aren't connected to another device. So, to summarize, router interfaces have the shutdown command applied by default, so they will be in the administratively down, down state by default. Switch interfaces do not have the shutdown command applied by default, so they will either be in the up state if they are connected to another device, or the down, down state if not connected. Now let's look at another useful command to check on switch interfaces. That is, show interfaces status. Let's look at each field of the output. First, the port field simply lists each interface. Next, you might be wondering what this name field is. Well, it's the description of the interface. I'm not sure why they called it name and not description, but we'll configure descriptions on these interfaces, and you'll see that it appears here. Next is the status field. As you can see, this is different than the status field of show IP interface brief. The 4 connected interfaces show a status of connected, and the unconnected interfaces show a status of not connect. There are other possible statuses. We'll cover them as they come up in the course. Next is the VLAN field. VLANs will get their own video. Basically, they can be used to divide LANs into smaller LANs.
Now, I understand VLANs. Where I get confused is trunk. Now, I do know what trunking is, but I get it confused and mixed up with VLAN.
As you can see, the default VLAN is 1. The only one that does not show a VLAN of 1 is F02, which shows trunk. I won't explain trunks now. They'll be covered in the VLAN video.
Oh, good.
Just take note of the fact that the interface connected to the other switch, switch 2, is a trunk interface. Next is the duplex field, which, as I mentioned before, indicates whether the device is capable of both sending and receiving data at the same time, which is known as full duplex, or if it's not, which is called half duplex. Duplex is auto by default on Cisco switches, meaning it will negotiate with a neighboring device and use full duplex if possible. Notice that all of the unconnected interfaces have a duplex of auto, and the connected interfaces have a duplex of A-full. Well, the A stands for auto, and it means that it automatically negotiated a duplex of full with the neighboring device. Next is the speed field, which is also auto by default. These are fast Ethernet interfaces, so they are capable of speeds up to 100 megabits per second. However, they are also capable of operating at 10 megabits per second. Auto means they are able to negotiate with the device they are connected to and use the fastest speed both devices are capable of.
Okay.
This time we see A-100, meaning a speed of 100 megabits per second was auto-negotiated with the neighboring device. I'll talk in more detail about auto-negotiation soon. Okay, finally is the type field. These are all RJ45 interfaces for copper UTP cables, but if they were small form factor pluggable, or SFP modules, you'd see that here instead. In this case, we see 10/100 base TX, the 10/100 of course referring to the speeds at which these interfaces can operate. Auto-negotiation works well, so usually you'll leave it be, But let's go and manually configure the speed and duplex of an interface, F01, which is connected to R1. As you can see, I enter interface config mode, and then use the command speed. I use the context-sensitive help to display the next option, and I can choose between 10 or 100 megabits per second, or auto. So I set the speed to 100, since R1's interface is a fast Ethernet interface also. Then, I use the command duplex to set the duplex of the interface. As the context-sensitive help shows, I can choose between auto, which is the default, or full and half.
Okay, so it's exactly like how I remember it being. Also, it's very similar to the router. So I always think of it like a skill tree. You come in and then it becomes enabled, and then it just kind of goes out from there, and different commands just lead to different branches of the tree. I don't know if that's how you should think about it, but that's how I think about it, because I'm sitting here thinking like, okay, we're in config T, and then so we went on this side, and then it's like, okay, interface F01, okay, then speed, and then so far and so forth.
Both switch 1 and R1 support full duplex, so I choose that. Finally, I configure a description on the interface, indicating that it is connected to R1. Okay, so when I use the show interfaces status command, once again, you can see both the configured description and the configured speed and duplex. Notice the duplex is full rather than A-full, and the speed is 100 rather than A-100, because they are not being auto-negotiated anymore. Once again, normally you will keep auto-negotiation on, but if perhaps there is some problem and it's not working, you should know how to manually configure the speed and duplex of an interface.
Okay, that makes sense.
Now let me quickly do some configurations for the other connected interfaces off camera. Okay, so I just configured descriptions on F02, 03, and 04. Now, how about the unused interfaces? Although the fact that switch interfaces are enabled by default is convenient, as you can just plug a device in and use it straight away, it can be a security concern. Really, you should disable the interfaces. Fortunately, instead of having to configure each of the 8 interfaces one by one, there is a way to configure all 8 interfaces at once.
Yes.
Here's the command that can save you a lot of time. From global config mode, type interface range, and then enter the range like this, F05 to 12. This time, instead of interface config mode, I am brought to interface range config mode, and I enter a description, and then shut down the interfaces. All at once, I get messages saying the interfaces have changed to administratively down. Now, before we check show interfaces status once more, let me show you a cool thing about this command. The interfaces in the range don't all have to be consecutive. For example, if I later want to enable Fast Ethernet 05, 6, 9, 10, 11, and 12...
I'm pretty sure these number signs don't matter. They're just there to show like a space, so that way you can read it better. I don't think that the number signs matter.
But leave 7 and 8 shut down. I can do this. Interface range, F05 to 6, comma, F09 to 12. Then if I issue no shutdown, you can see only those interfaces are enabled. F07 and 8 remain down. Okay, so I shut down interfaces F05, 6, 9, 10, 11, and 12 again, and here's the output of show interfaces status again. Now you can see the description of each interface, and the status is disabled. Once again, this status is different than the status shown in show IP interface brief, which will now be administratively down, although really, they mean the same thing. Before talking about auto-negotiation, I want to explain full and half-duplex. I have briefly mentioned it a few times, but haven't explained it in depth yet. Half-duplex means that the device cannot send and receive data at the same time. If it is receiving a frame, it must wait before sending a frame. Full-duplex means that the device can send and receive data at the same time. It does not have to wait. Clearly, full-duplex is the preferred way to go. In modern networks that use switches, all devices can use full-duplex on their interfaces. So, you may be wondering, where is half-duplex used?
Hubs.
Well, in modern-day networks, almost nowhere. But to understand half-duplex, let me introduce you to an old type of network device, which was around before the network switch. The hub is much simpler than a switch. In fact, it is simply a repeater. Any frame it receives, it floods like a switch does with a broadcast or unknown unicast frame. For example, if PC1 wants to send a frame to PC2, it will send the frame out of its network interface, and after the hub receives it, it will repeat the frame out of its other interfaces to PC2 and PC3. PC3 will recognize that the destination MAC address is not its own and ignore the frame, and PC2 will receive it normally.
It's crazy how technology
Now, what if two PCs try to send frames at the same time? In this case, PC1 is trying to send a frame to PC2, and PC3 is trying to send a frame to PC1.
Like, why would
they both send the frames out of their network interfaces, and this is where a problem occurs. The hub won't send one first and then send the other after. It simply tries to flood both at the same time, and this will result in a collision on the interface, and PC2 won't receive either frame intact.
Here to get to the next place,
all devices connected to a hub are part of what's called a collision domain. The frames they send could collide with frames any of the other devices connected to the hub send. To deal with collisions in a half-duplex situation like this, Ethernet devices use a mechanism called CCNA CD. Let's check it out. CSNA CD stands for Carrier Sense Multiple Access with Collision Detection. It describes how devices avoid collisions in a half-duplex situation, and how they react if collisions do occur. It works like this. Before sending frames, devices listen to the collision domain until they detect that other devices are not sending frames. If a collision does occur, which can still happen because of bad timing and such, the device sends a jamming signal to inform the other devices that a collision happened. Each device then waits a random period of time before sending frames again. The process then repeats, with each device listening to check if other devices are sending frames before sending their own frames.
So it's just like a highway.
Now, that process works, and it was how networks operated for a long time. But switches are more sophisticated than hubs. Hubs are simple repeaters which operate at layer 1, repeating whatever signals they receive. Switches operate at layer 2, using layer 2 addressing, MAC addresses, to send frames to specific hosts. They also won't try to send 2 frames to the same host at once. So this network, which was 1 collision domain when connected to a hub, is now 1, 2, 3 collision domains.
Wow.
Because of the improved functionality of switches over hubs, these devices can now operate in full duplex, meaning they don't have to worry about whether or not other devices are sending data at the same time. They can send data freely.
It's just all isolated.
Although problems like collisions still do occur, they are rare and usually are a sign of a problem like a misconfiguration, rather than a regular occurrence, like in a half-duplex network. So let's review half and full duplex once more. In half-duplex, the device cannot send and receive data at the same time. If it is receiving a frame, it must wait before sending a frame. Devices attached to a hub must operate in half-duplex. In modern networks, you're probably not going to use a hub, but it's a possibility. In full duplex, the device can send and receive data at the same time. It does not have to wait. Devices attached to a switch can operate in full duplex. Okay, now that you know what duplex is, let's talk about speed and duplex auto-negotiation on interfaces. And this applies to both routers and switches, by the way. Interfaces that can run at different speeds, for example 10/100 or 10/100/1000, have default settings of speed auto and duplex auto. Interfaces advertise their capabilities to their neighbors, and they negotiate the best speed and duplex settings they are both capable of. So let's look at an example. Here's a small network, a switch with 3 PCs connected. Connected to G01 is a PC with a regular Ethernet interface. Connected to G02 is a PC with a fast Ethernet interface. And connected to G03 is a PC with a gigabit Ethernet interface. As you probably know by now, an Ethernet interface can run at 10 megabits per second, a fast Ethernet interface can run at 10 or 100 megabits per second, and a gigabit Ethernet interface can run at 10, 100, or 1000 gigabits per second. So, G01 and the PC will negotiate to a speed of 10 megabits per second and full duplex. G02 and the PC will negotiate to a speed of 100 and full duplex. And G03 and the PC will negotiate to a speed of 1000 and full duplex.
Dope.
The PCs are all able to use the max speed of their network interfaces, and the switch adjusts the speed of its interfaces to match. In a network like this with all PCs and switches, there's no reason to use half-duplex, so they all negotiate to use full duplex.
Wow.
Now let's talk about another situation. What if auto-negotiation is disabled on the device connected to the switch? So the switch is trying to auto-negotiate, but the other devices don't respond. Well, this is how the switch will respond. For the speed, the switch will try to sense the speed that the other device is operating at. If it fails to sense the speed, it will use the slowest supported speed. For example, 10 megabits per second on a 10, 100, 1000 interface.
Throttle itself.
Now, as for duplex, if it ends up using a speed of 10 or 100 megabits per second, the switch will use half-duplex. If the speed is 1000 megabits or greater, it will use full duplex. So let's see how this works. In this case, only the switch is using auto-negotiation, and the 3 PCs have manual, fixed speed, and duplex settings.
Okay.
We'll also assume that the switch successfully detects the speed that the PCs are using. The green PC has a speed of 10 megabits per second, so the switch detects that and sets its speed to the same. Because its speed is 10 megabits per second, it sets its duplex to half-duplex. Now, how about G02, connected to the red PC? It senses that the PC is using a speed of 1000 megabits per second, so it uses the same. Because the speed is 1000 megabits per second, it uses full duplex. Now, how about G03, connected to the blue PC? It senses the speed of 100 megabits per second, but then what about the duplex? The PC is using full duplex, but without auto-negotiation, the switch can't sense that. So, because the speed is 100 megabits per second, the switch uses half-duplex. This results in a duplex mismatch, which will cause collisions to occur, resulting in poor network performance. So really, you should be using auto-negotiation on all devices in the network.
That makes sense.
Now, let's take a look at some of the errors that can show up on interfaces that otherwise seem to be working.
Fast, Ethernet,
the switch will take count of some of these things, and you can view them with the Show Interfaces command. We took a quick look at this command when we were configuring router interfaces, so these things aren't specific for switch interfaces. This time, let's focus on some of these statistics at the bottom.
Receive 6 broadcast.
There are lots of different kinds of counters shown here, and you don't have to know all of them at this point. So let's just focus on some. First up, not errors, but you can see the total number of packets received on the interface and the total number of bytes in those packets. Next up is runts. These are frames that are smaller than the minimum Ethernet frame size of 64 bytes. Beside the runts counter is the giants counter, which counts received frames which are larger than the Ethernet maximum frame size of 1518 bytes. Next up, CRC, which counts frames which failed their CRC check. If you remember, the CRC is the cyclic redundancy check, done via the FCS, or frame check sequence, in the trailer of an Ethernet frame.
It's making sure that
it's
all
used
the
to
frames
detect
got
errors,
where they need
and
to
if an
go.
error is detected, this counter goes up.
Yeah.
Next is frame, which counts frames that have an illegal or incorrect format. Input errors is a total of various counters, including the 4 I just mentioned. Finally, output errors counts frames the switch tried to send, but failed due to an error. Keep in mind, I'm showing you all of these counters on a switch, but they are the same on a router. Before moving on to today's quiz, let's review what we covered. We talked about interface speed and duplex. I explained the concepts of full and half duplex. Full duplex is preferred, and in most modern networks, all devices will be able to operate in full duplex, so they can send data freely without waiting for other devices to stop sending.
Man, I need caffeine.
We talked about speed and duplex auto-negotiation, which allows devices to find the appropriate speed and duplex settings without manual configuration. We looked a bit at interface status, using the show interface status command, such as the statuses connected, not connect, and disabled. We'll look more at this throughout the course. Finally, we looked at some interface counters and errors, such as runts, which are frames that don't meet the minimum size requirements, and giants, which exceed the maximum frame size requirements. Okay, let's get started on the quiz. Remember, there will also be flashcards which you can download from the link in the description to help you remember what you've learned in this video. Let's go to question 1.
I don't know when we're doing, but we're going to do
There is a duplex mismatch between switch 1's F01 interface and switch 2's F01 interface, which are connected. Auto-negotiation is disabled. What will be the result? A. Improved performance.
No.
B. Collisions will occur.
Collisions will occur.
Or C. Switch 1 will sense switch 2's duplex setting and adjust to match.
So there's a duplex mismatch between switch 1 interface and switch 2 interface, which are connected. Autonegotiation. No, it's not going to sense anything. It's going to be, there's collisions are going to occur.
Pause the video to think about your answer.
I just did. That's what we did.
The answer is B. Collisions will occur.
Ooh.
The half-duplex side is unable to send and receive data at the same time. However, the full-duplex side is unaware of this and will send data even if the half-duplex side isn't ready to receive it, causing collisions. So B is correct. It definitely won't result in improved performance. In fact, performance will probably be much worse, so A is incorrect. Switch 1 won't be able to sense switch 2's duplex setting without auto-negotiation enabled, so C is incorrect too. Let's go to question 2. What is used on half-duplex interfaces to detect and avoid collisions? A. CSNA-CD. B. CSNA-CA. C.
No,
Auto-negotiation.
CD.
Or D.
Wait, hold on. What is used in half-duplex interfaces to detect? Oh, yeah, the CD.
Duplex auto. Pause the video to think about your answer.
Auto-negotiation is like not that. It's like
the answer is A.
After.
CSNA-CD.
Yeah.
CSNA-CD stands for Carrier Sense Multiple Access with Collision Detection. It describes how devices using half-duplex listen for activity on a network segment and then send data only when other devices aren't sending. It also describes how a device will react when a collision does occur. So A, CSNA-CD is correct. B, CSNA-CA, is a similar concept that we'll cover later in the course that stands for Carrier Sense Multiple Access with Collision Avoidance. C, auto-negotiation, and D, duplex auto, are unrelated to how a half-duplex interface detects and avoids collisions. Let's go to question 3. Which command shows various counters of errors detected on an interface? A, show interfaces. B, show IP interface brief. C, show interfaces status. Or D, show interfaces errors. Pause the video to think about your answer.
Status, I believe. No, the status shows you if it's up or down. Show interfaces, I think, is incomplete. Show interface brief shows you all the information of that thing. It might be errors.
The answer is A, show interfaces.
Shit.
Let's check the output of each command. As you can see, show IP interface brief doesn't display any counters of errors detected on the interface.
Yeah, it just shows you.
It's a useful command for checking the IP addresses of interfaces, checking if they're shut down, etc. Show interfaces status also doesn't show any error counters. It gives some basic information about interfaces such as description, status, duplex, and speed. Show interfaces errors isn't a real command, so an error message appears when I try to enter it.
Okay.
Show interfaces displays counters of errors detected on the interface. In this case, I used show interface F01. Because so much information is given for each interface with this command, you probably won't use this command to view all interfaces at once, but rather specify an individual interface to check. The counters are at the bottom of the output.
Yeah.
So A, show interfaces, is correct. Let's go to question 4. Which are examples of errors that might occur on a network interface?
Let's go.
A, runts, giants, broadcasts. B, shorts, longs, oversizes. C, packets, bytes, inputs, outputs. D, runts, giants, CRC.
Runts, giants, CRC. I don't think broadcast is going to be an issue. This is nothing. Packets, bytes, inputs, and outputs, those are real, but I don't think that's it. The CRC is probably the biggest one because that determines if anything was wrong with the packet.
Pause the video to think about your answer.
Ooh, it's what we just did.
The answer is D. Runts, giants, CRC.
I'm too
The
good.
names in B and C are not real errors that can occur on an interface. In option A, runts and giants are possible errors, but broadcasts are not errors. They are part of normal network operations. So D, runts, giants, CRC, is the correct answer. Remember, runts are frames that are too small, giants are frames that are too big, and CRC counts the frames that failed their CRC check, which is done in the frame check sequence in the trailer of the Ethernet frame. Let's go to question 5. Switch 1 is trying to auto-negotiate interface speed settings with Switch 2. However, auto-negotiation is disabled on Switch 2's interface. Switch 2's interface is configured with a speed of 100 megabits per second and full duplex. What speed and duplex settings will Switch 1 use? A. Speed 100 megabits per second.
Sorry, I wasn't paying attention. I was jacking with other shit on my desk because I can't focus because I need caffeine. Anyway, those are excuses. SW1 is trying to auto-negotiate interface speed setting with SW2. However, auto-negotiation is disabled on SW2 interface. SW2 interface is configured with a speed of 100 and full duplex. What speed and duplex setting is SW1 using? Assuming it's going to use the bare minimum
second
of
duplex
what
full.
It senses.
B. Speed 100 megabits per second, duplex
A.
half. C. Speed 10 megabits per second, duplex full. Or D. Speed 10 megabits per second, duplex half.
Now, it might do
Pause
a
the video to
half
think about your
duplex
answer.
because it doesn't know.
The answer is B. Speed 100 megabits per second, duplex half.
So it's going to be able to sense the speed, but it doesn't have a way to sense if it's duplex. So it's just going to assume that it's half duplex because it doesn't want to have any collisions.
If the remote device has auto-negotiation disabled, but it's enabled on the local device will attempt to sense the speed the remote device is using. So, Switch 1 will be able to correctly set its interface speed to 100 megabits per second to match Switch 2's.
Yep.
However, it can't sense the duplex mode of Switch 2's interface. So the rule is, if the speed is 10 or 100 megabits per second, half duplex will be used. Otherwise, full duplex will be used.
All right.
In this case, half duplex will be used, which will result in a duplex mismatch between the two devices, and probably poor performance on the link between them due to collisions. Okay, that's all for the quiz. Remember to make use of the supplemental materials for this video.
All right, we're about to do the
I've
packet
made a set of
tracer.
flashcards to be used with the Anki flashcard software to help you remember what you learned in this video. Also, there will be a packet tracer practice lab to give you hands-on practice configuring Cisco devices. That will be the next video. Good luck with your studies. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or basic attention token tips via the Brave browser. That's all for now.
Ooh, that's cool. Yeah, he's amazing. He's really, really good. So if you're not already subscribed to him, you definitely should be. Oh, it's the same video. We're gonna do some IPv4 subnetting in a second as well. Okay. We're gonna use my amazing worksheet here that I have. I'm super pumped about using this. Okay, I made it last night. Anyway, before we get there, we have to do this. So let's figure out and see what's going on with this. His packet tracers are never too complicated, but they're really good to reinforce the skills or the concepts that he was just talking about. So let's look here and see what's going on. Let's see if we can figure it out a little bit before we watch the video. So we're going to configure the host names of R1, S1, and SW2. So then we're going to configure the appropriate IP addresses on R1, PC1. Do we have... Oh, yeah, we do. We have this right here. And we have what the other parts are supposed to be, I think. Or maybe we're just supposed to subnet it. Ooh, does that mean I could use my thing? We might use my thing. Okay. Configure the appropriate descriptions for each interface. Disable interfaces which are not connected. This is a really good one. Let's watch it through.
Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA 200-301. If you like these videos, please subscribe to follow along with the series. Also, please like and...
Oh, I totally forgot that you guys can't see my... What is happening? Hello? Hello? There it is. Okay, we're good. So because before you couldn't see this, but now you can. Okay, anyway.
Leave a comment and share the video to help spread this free series of videos. Thanks for your help. In this lab, we'll configure interfaces on a router and 2 switches. This is a single LAN, 172.16.0.0/16, connected to R1's G00 interface. In the real world, R1 would then connect to other LANs or perhaps the internet, but we'll just configure this small LAN for now. Let's get started.
Let's do it.
So there are 6 main steps in this lab. 1. Configure host names. 2. Configure IP addresses. 3. Configure speed and duplex. 4. Configure interface descriptions. 5. Disable unused interfaces. And 6. Save the configuration.
It's a good package
We'll go through each step one by one. I'll go through the steps one device at a time, but you can do it in any order you like. So let's go on R1 first.
Ooh.
The first step is to configure the host name. As you can see, it currently has the default host name of the router, as indicated by the prompt.
Man, I forget these so easily.
Enable to enter privileged exec mode, then configure terminal to enter global config mode. From here, simply type host name R1, and you can see the prompt has changed to indicate the new host name. Now let's configure the IP address on its G00 interface. Type interface G00 to enter interface config mode for the interface. Actually, before doing the configuration, let's confirm the current status of the interface. Do show IP interface brief. Remember, do lets me use the show command, even though I'm not in privileged exec mode. Here's the gigabit Ethernet 00 interface. The IP address.
I wish that it told you what interface you were in. Like, I get it, that's config interface. Okay, that's awesome. But, like, would it kill it to add, like, a G0 or something next to it? Like, anyway.
Is unassigned, so the method is unset. And the status is administratively down, because that's the default setting for router interfaces. Let's and then check again after. So, let's configure the IP address.
Alright, now hold on. Okay, that's a little bit better. Just so that way we kind of went over it. So we enabled it. Then we went to config T. Then I should have done, was it space or something to finish the command? I didn't. So host name R1, it immediately changed. Then I did interface G, that's what INT stands for. It stands for interface. G0/0. So now I'm in that interface. And I put do show IP interface brief. So this is the interface. This is the IP address. There is none because I haven't assigned anything yet. Here's port 1, port 2, port 3, 0, 1, and 2. Nothing's been assigned, unset, administratively down. Because routers and switches are different. They're not automatically up. Switches are automatically up. Routers are automatically down. That is why the router you get from your ISP might have multiple ports, but you have to pay that money for them to activate it. I wonder if I could just activate it. That might be illegal. Anyway.
IP address 172.16.255.254, and because the prefix length is /16, the subnet mask will be 255.255.0.0.
Okay, now hold on. Where did he get this? 250. Okay, so because these are the parts that are interesting because those are what's there. So 172.16.255.254, and he's using the gateway, the default gateway, which I think one is always reserved for the default gateway. Anyway. 255.255.0.0. Sweet. Okay. I hate that there's not a confirmation with it either. Let's look at something real quick. So if this is 172.16.0.0, let's go ahead and let's use my thing because I'm super excited about it. It'll make this packet tracer a little long, but it'll be a good use of examples. Yeah. Okay. So, what this is it supposed to be like this little cheat sheet. Well, it's not really a cheat sheet. It's just a worksheet to help you be able okay. So here's how it's supposed to work. You come over here and you type in, where'd my, what? There we go. All right, you write it in. So it's 172. 16 0. That doesn't look like a 0. It looks like a G. 0 0. So then we use this to put tally markers to figure out 172. So 170 or 128 plus 64 is 4. That would be 13. Carry the 1, 6, 3, 9. Crap, just give me my phone. So 128 plus 64, 192, that doesn't work. Plus 32, that works. So, whoa. So 0, 32 plus 16, it's 176, so it's not going to be 16. Okay. Plus 8 is 168. Okay. Plus 4 is 172. Boom. So then we just kind of put a mark next to all these that were used. You don't really need this part. I did it because I thought it looked cool. Okay, and then we have 16. So here, and then everything else is zeros. And then we have 16, right? So we count them. This is 8, 8, 16, so we draw a line. Whoa, dang it, dude. What's going on? Okay. Stupid buttons on my little pad. Okay. So that means that this side is frozen. And this side is free. So the network bits that are frozen is 16. That means that the side R is 16. Okay. So let's build the mask. Well, no, let's go over here. Okay. So the host bits that are free is 8, which means that we have 255 plus 255 minus 2. So does that mean that we have 500 508 free addresses, and usable hosts is 2 because we have the network. So the network is 17. Man, dude, this is a lot smaller than I thought it was going to be. Thought this was going to be a lot easier, right? 172 16 0 0. That looks like a 6, dude. There we go. So that means our very first host is going to be 172. That looks like a 9. What is going on? Why do I suck? 172 16 0 1, right? And then our last host would be 172 16 255 254. And that makes sense because our last host that we just did was this guy right here. Okay, right there. Our broadcast would be all exactly the same, except it's going to be 255. And then the next subnet should be 172 17 0 0. Okay. So the only one I'm not sure I did correctly was this, but I'm pretty sure I did. Although I think that I'm supposed to have way more than that. I don't know. Okay, anyway. Let's get back to the packet tracer. All right. Which is why we used 25 255, because we're able to. That is within the scope of this 16. Now, how you were supposed to know that without knowing how to subnet and how that, I have no idea. Probably not. You're probably supposed to figure that out. Okay. No, I used the wrong one. I used the wrong address. There we go.
Okay, now because this interface is connected to another networking device, switch 1, I'll manually configure the speed and duplex. Speed 1000, meaning 1000 megabits per second, because this is a gigabit Ethernet interface. Then, duplex full. Devices attached to switches can use full duplex. There's no reason to use half-duplex like a device attached to a hub. Next, let's configure a description. I'll indicate that this device is connected to switch 1, so description to switch 1. Now, the last step is to disable interfaces which are not connected to other devices. Because router interfaces are shut down by default, we don't have to do that. However, we do have to do the opposite for this interface, which is connected to another device. So, no shutdown. There we go. Now the interface is enabled, and let's check out the status. Do show IP interface brief. Okay, you can see the IP address we configured. The method is...
Okay, now hold on. The description is no shutdown. And why did we do that? Why do we make the description no shutdown?
Which are not connected to other devices. Because router interfaces are shut down by default, we don't have to do that. However, we do have to do the opposite for this interface, which is connected to another device. So, no shutdown. There we go.
Oh, this was the description. Okay, so maybe these things matter. I guess we'll figure that out in a second. Okay, and then just no shutdown. We already know that. Okay, so that is the thing. Okay, link gigabyte 1 create status is up. Okay.
Now the interface is enabled, and let's check out the status. Do show IP interface brief. Okay, you can see the IP address we configured. The method is manual, the status is up, but the protocol is down. Although on a real Cisco device, I think this should be up.
Okay, now hold on. He was able to do ip int. Oh, I didn't do int. Okay. I was like, but I didn't spell out brief, and then I get slammed. Like, what? I'm still getting slammed. Why? Do show. I forgot IP. There it is. Okay. So here's the IP address. Up, manual. Okay.
On packet tracer, it's down because I manually configured the speed and duplex. Device is manual. The status is up, but the protocol is down. Although on a real Cisco device, I think this should be up. On packet tracer, it's down because I manually configured the speed and duplex on this interface without doing so on switch 1's interface, but we'll fix that soon. That's the downside of using a simulator like packet tracer. Sometimes things don't behave like they should on a real device. Before moving on to switch 1, I'll configure descriptions on R1's other interfaces to indicate that they are not in use. I'll use the interface range command. Interface range G01 to 2. Description not in use. Okay, let's check our config. Do show run. Here's the running config of the device, and here are the configurations of the interface.
Hold on. What do you do? Did I do that correctly?
Do show run. Here's the running config of the device. Use.
Hold on. Damn it. Okay, yes. So we're just in the range. We're in the interface of just looking at those from 1 to 2. And now we're looking in the description. Not looking, we're making the description. So description not in use. He only put one. See, I don't know what those hashtags mean. I don't know if that's just for ease of seeing or what.
Okay, let's check our config. Do show run. Here's the running config of the device, and here are the configurations of the interface, including speed, duplex, IP addresses, and descriptions. Okay, since I'm done configuring, I'll use end to return to privileged exec mode. Now let's save the running configuration. There are 3 Cisco devices in this lab. I'll use a different method.
Yeah, I think that these are just to make it easier to see. Yeah, not in use. Yeah, that's what it is. That's exactly what it is. I don't think they really serve any other feature, which is fine. Okay. And the only reason I hit enter like a shit ton of times is to kind of make it easier for my eyes to be able to see. So then we need to save. I think we can do save running config.
Method to save the configuration on each device to show you each one. Here on R1, I'll use copy running config startup config and hit enter to confirm. Now let's check it.
Okay, so start. Really? Copy running config. Oh, because there it is. My fat fingers. Destination file. Okay, yes. Okay.
It was saved to the startup config. Show startup config. Here are the interfaces, and you can see the configuration changes we made. Okay, that's all for R1. Before moving on to...
Isn't that supposed to have a space?
It was saved to the startup config. Show startup config.
Dang it. Yeah. Okay, we're good. Because if it didn't save, the stuff wouldn't be there.
Here are the interfaces, and you can see the configuration changes we made. Okay, that's all for R1. Before moving on to switch 1, I'll make the only configuration change we need to make on the PCs, configuring their IP addresses. Let's go on PC 1. Click on config, and notice I pre-configured the...
Okay. So this is within the scope. But is this not the same? No, that's the default address. But shouldn't I just use DHCP?
The gateway, which is R1's address, because it's the router for the network. Now click on Fast Ethernet 0, which is PC1's network interface.
Crap. Okay, so that's the global. So this is that port. Okay.
PC1's IP address is 172.16.0.1.
Because that's the first one that's possible to use. Ooh, look at me. I can ride my bike with no handlebars. No handlebars. I understand this stuff. I'm just really slow.
Hit tab, and it automatically fills in the appropriate subnet mask 255.255.0.0. Okay, now I can exit out. Next is PC2. Click config, Fast Ethernet 0.
Okay, we're going to try to do this on our own here. Okay, default gateway is good. So then this should be 172.16.0.2, right? There's no reason why it can't be that. Fantastic. And then we'll do the same thing for this one. 172.16.0.3. Good. And then we shall do the same. 172.16.0.4. Now, theoretically, I could have used anything between like 1 and like 254, but it just makes sense to do it this way.
IP address 172.16.0.2. Hit tab and it fills in the subnet mask.
Yes.
PC3. Config. Fast equal at 0. IP address of 172.16.0.3. Hit tab to fill in the subnet mask and exit. Finally, PC4. Config. Fast equal at 0. IP address of 172.16.0.4. Hit tab to fill in the subnet mask and exit.
Yes. Woo!
Okay, now let's configure switch 1. Enable.
Now hold on. Let's see how far we can go by ourselves here, boys. So we want to go to enable. Then we need to go to host name. Nope, there's no space. Host name SW1. Damn it, why didn't that work? We didn't get far, boys. Oh, damn it, we gotta be config. Okay. And then now we go to hostname SW1. Ooh. Now, what we need to do is that we have to configure all 4 of these ports, I believe. Or maybe it's just the 2 gigabyte. No. Well, they're already up by default. So then we just have to make sure that they're full duplex. We also have to make sure that they are the auto stuff is correct. So I would imagine that the show the brief would probably be the answer.
Hostname switch 1. Now let's check out the interfaces. Do show interfaces status.
Okay. Damn it. Okay. So we have fast Ethernet 1 and 2 are connected. We have auto duplex. We have auto speed. We're golden. For these 2 that are going to the computers, we're good. And we can even see that it's green, so we're good. We have problem with the gigabyte. Gigabyte 1 is not connected, so we're gonna have to fix that. We're gonna have to get in there. So I would imagine that it's interface. Is it just G0/0? Okay. Then we just make it go up. Is it really that simple? I feel like that's not that simple.
This is a command that works on switches, but not routers. As you can see, all default settings. No descriptions.
There's no way it's that simple.
Not disabled, because these are switch interfaces. They're not shut down by default. The speed and duplex are auto and auto as well. Okay, let's configure the G01 interface. Interface G01, speed 1000, duplex full. It's connected to...
Okay. So it wasn't what I thought, but it's still pretty easy. Speed 1000. Why is that? Why is that invalid? His wasn't invalid. I entered in. Oh. Because that is the interface. So I went into an interface that doesn't even exist. Interesting. Duplex full. Okay. And then our description is we're trying to give a description of where this port goes to. So description, boom, boom, to R1. End. Then we want to copy running startup config. I think that's it. And then we just saved it.
Now G02. Interface G02. Speed 1000.
Crap, I forgot to do it with that. So then we need to go into interface G0/2. Why is that invalid? Config T. Then, because we got to get into config T, then we go to interface 0/. Okay. Then we look at speed 1000 and duplex full. Why protocol interface internet changed to status down? Why was it changed to status down? I didn't do that.
Duplex full. It's connected to switch 2, so description to switch 2.
Okay, maybe that just does that. Description. Okay, and then end. And then copy running config startup config.
Now, as for Fast Ethernet 01 and 02, they're connected to end hosts, so according to the lab instructions, I don't need to configure the speed and duplex. So I'll just configure descriptions. Interface range F01 to 2.
Okay. Config T. Range F0/1 to 2. And then we want description. I don't think caps locks matters. I don't think so. What's the description he's gonna put?
Description to end hosts. Yeah.
Oh, to end host. Okay. And I've noticed that he only uses one hashtag for like gigabit and uses two hashtags on the end for fast Ethernet. I wonder if that's like a him thing or.
Now, as for the rest of the interfaces, I'll configure descriptions and shut them down. There are 22
22
interfaces. So, interface range F03 to 24. Description not in use.
Okay, because we're gonna shut them down. We're gonna shut them down. So I can just hop between these things. I can go from the range here. Whoa, no, go back. I wasn't ready. Okay, I can go from the range 02 straight to range there. There's nothing else special I gotta do. Does that mean that I can just reuse this and go from 3 to / what was it, 24?
24. Description.
So description's gonna be down, not in use.
Not in use.
Now I can put whatever I want in the not in use, but I'd rather do what he does, so in case I screw up. Well, now hold on.
24. Description not in use.
Oh, and then he just did shutdown. Because we're in the interface of them. Yes. Okay, this is making sense. So here's all the interfaces. You can see them right here. And they're all getting shut down.
Okay, let's check the configurations.
Well, before we do that, and copy startup. Was it a copy startup? Copy startup running config. Okay. So now we need no way, it doesn't. Oh, it only has it from there. Okay. Oh, I hate when it does this. Oh, there's like a button or something that you can hit. And this happens to me all the time, too. Hold on. Let's ask Google real quick. When putting in incomplete or wrong commands in a Cisco switch or router, it'll say translating and then the wrong command, and then it will say the domain server, and it'll just take forever to process. What is the hotkey to get it to stop processing? Control-Shift-6. Yes. Oh my gosh, dude, that's so... Like, I'm surprised that doesn't happen to a lot of people, but like that happens to me all the time. Maybe I'm just an idiot. Okay, config T. And then we want to be in this range. Do show. Is it brief?
Do show interface status.
No, interface status. Okay. To end host, connectivity. Okay. And then they're all disabled. Okay. But this is connected. But this is not connected. Why is that not connected? Oh, but it says, it doesn't say disabled. It says not connected. So maybe we need to put that up in the other switch.
Okay, you can see the interfaces we disabled. Again, because I configured the duplex manually on G02, it's down at the moment, but it will come up when we configure switch 2. Notice the speed and duplex we manually configured. This is also a problem with packet tracer. It says A-1000 and A-full, meaning it auto-negotiated the speed of 1000 and duplex of full, which is incorrect because we manually configured it. On a real Cisco device, this will say simply 1000 and full, without the A. Anyway, I'll type end to return privileged exec mode. Now let's save the configuration. This time, I'll use write memory. Okay, let's check the startup config. Show startup config. Okay, you can see the changes we made to the interfaces here. Let's go on to the last device, switch 2. Enable, conf T, hostname switch 2. Let's check the interfaces. Do show interfaces stat.
Hold on, I'm sorry. I was thinking about things I shouldn't have been thinking about.
Changes we made to the interfaces here.
Yep.
Let's go on to the last device, switch 2.
He didn't save his configurations, buddy. It's not good. Okay. So I should be able to do a lot of this. Let's see. So enable. We're ignoring the passwords right now, FYI. So config T, host name is going to be SW2. Then we need to configure that. So we need to get into interface G0/2. And then can we just put up? No. How do we make it go up? How do we enable it?
Enable conf t hostname switch to. Let's check the interfaces. Do show interfaces status. As you can see, all the defaults again. Now the configurations we will make are the same as for switch 1, except switch 2 has only one active gigabit Ethernet interface, G01. So I'll run through the configurations. Interface.
Oh shit! I'm in the wrong interface. Config T. Yes. Okay, now I'm in the right interface.
G01, speed 1000, duplex full. Description, 2 switch 1. Interface range F01 to 2. Description, 2 end hosts.
Okay, hold on. He jumps between the interfaces like it's nothing, and I guess it is nothing. F0/1 to 2. Okay. Description to end host. Okay. And then no. Then we're going to go to range 3 to 24. Shutdown. Okay, config T. Do show. No, isn't it supposed to like tell me what the other possible commands are? Crap, what isn't it? It's not brief. I need to know if the G1 is up. Okay.
Now let's shut down the other interfaces all at once. Interface range G02 at 03 to 24. Description not in use.
Oh, I didn't shut down G02.
Do show interfaces status.
That's what it is. Do show interface status. Okay, that was enough. Okay, so those are connected. Everything's disabled. So then how do I connect G1? See, his is connected. How is it connected? Did I disconnect it somehow? Okay. No, in the terminal, damn it. Enable. There it is. That's what I forgot to do. So let's go to interface G/1. No shutdown. No, I just did the command, damn it. Okay, hold on. Let's X out. Let's calm down. Let's calm down. Let's calm down. Okay, config T. Okay. And then we're going to go into interface G/01. Okay. And we're going to do no shutdown. Okay. Okay, no shutdown. We have a cable. So then if I do show crap, dude. Interface stat. Still not connected. Okay, I did that, but when I displays it means the physical layer link is down even through configure no shutdown. So it's saying that's not plugged in, but it is plugged in. So is it just stupid?
It's of A-full. On a real Cisco device, this will be 1000 and full without the A, because these settings were manually configured, not auto-negotiated. Finally, let's save the configurations. And this time I'll just use write to save the configuration. Now let's check. Show startup config. Looks like our configuration changes were applied. That's all for this lab. Thank you for watching.
Hold on. He used right? Oh, he exited.
Now let's check. Show startup config.
Yeah, show startup config. Yeah, all of our stuff's there. That's weird. It's all there, but it just shows that it's not connected. Okay. We're not going to get hung up on it. We're going to call this one done. It's also not showing any type of arrows either. I think Packet Tracer's having a moment. Okay, no, I do not want to save that. Alright, now we're moving on to this. Okay. The reason I'm doing this in Photoshop is because I can do this. I can just trash this layer and then make another one. Okay, so let's talk about this thing and what it is and why I think it's cool and stuff. Okay, so and we'll zoom in again. Maybe it's a little too much. There we go. That's perfect. Okay, so I actually have one that's already filled out, so we can kind of walk it through to kind of see like how it works and stuff. So basically, the way it's supposed to work is that it's supposed to be like a little worksheet, so that way it helps you work out like the what you call it. Hold on, I gotta put the pin in the right spot, otherwise I hit those stupid buttons that are on there. Okay. Ooh. Let's Yes. Is there a way to save it? It just, is it just always is now? Yeah, this is why I was having issues earlier. Okay. Anyway, the way it's supposed to work is that you're supposed to like kind of put the little marks here, so that way you can see what the binary is, right? And then the X's are supposed to show you which bits are frozen, not which bits are being used in terms of the binary. But which bits are used to be frozen. And that's what this line is. This line right here shows you that those are the frozen bits. Okay? This is the wild card. And if you don't know what a wild card is, so we have one. I could have sworn I just changed this. Yeah. So here we have this stuff. Looks like a 6. I hate when I write my zeros and they look like a 6. Okay, so 1 plus 2 is 3. Oh, yeah, 1 plus 2 is 3, and 3 plus 4 is 7. So this is 7. And then all of this combined is 255. Because what we're counting at, where we're adding is these. We're adding the X's. So all of that combined right here is 255. So that is our wild card. Okay. So the way we built this mask, the way we build the side R, is that we add up the frozen bits, and that tells us where we're at. So each one is an octet, right? So we have 8. So we have 8 bits. 8 bits, 1, 2, 3, 4, 5. 5 bits. And that's why it's 8 plus 8 plus 5 plus 0 equals 21. So that's the side R. Again, I don't know if I'm saying that correctly. I've never heard anyone actually say it. I'm just kind of doing it, just reading it. Okay. So now we have the subnet. We have our subnet mask. If we look here, these are the interesting, and you know what? I'll change my thing again. That's fine. If we look here, we have the interesting octets. So what does that mean? That means that it's the third octet that is split. That's this bad boy. Because it's split right here. Okay? Some of its bits are frozen. Some of its bits are not. Okay? And then we ask ourselves, what's the block size of it? How far apart is the subnet? And it's 8. 8 blocks. Okay? Because the mask equals, mask equals 256. Okay? So we subtract 256 minus the mask. Okay? So then what is 256? That is not 8. What am I doing? How do we get 8? I just confused myself. Yeah, I just confused myself. Dang it, dude. I was doing so well, too. Minus 256 minus the mask. Well, 256 minus the mask is not going to be 8. Unless. Okay. Hold on. Follow me for a second. Okay, so that's 5. That's 3. And that's 2. So 253, 255. If we change that to binary, would that be 8 bits? Well, no, it wouldn't be. Because that would be the full octet. No, I'm still confused. Dang it. Okay. We're gonna go to my good friend Claude. I don't know if you've heard of Claude or not, but he's a good friend of mine. Claude is smart. He's unemotional. This is actually how I built this thing. I asked it a whole bunch of questions because I wanted to build like this was my original sketch. I was like, hey, I think this might do really well with me trying to learn like subnetting and stuff. Can you like make it into a PDF? And it was like, of course I can. Okay, let's see here. I don't understand block size and target our octet round down. I don't understand block size and how it is 8. And I also do not understand target octet round down and how it's 208. All right, let's see what it says. And then we're going to do like 1 or 2 of these, and then we'll do the Anki cards.
Two questions. One, answer really. Let me take them in order. Why the block size is 8. Look at the third octet skit row and find the last frozen bit. For /21, that's the 1 in the 8 place. 128, 32, 16, or 421. To the power of, to the power of, to the power.
No, I don't need that.
That last frozen bit is worth 8. It's the smallest amount the network part of that octet can change by. Flip it, and the octet jumps by 8. Anything smaller, 4, 2, 1, is host space.
Anything else is host space. But no, it's 7.
Space. And changing those doesn't move you to a different subnet. It just moves you to a different address inside the same one. So block size equal to the place value of the last frozen bit. That's why /21 gives 8. If /22 froze 1 more bit, the last frozen bit would be the 4. And
oh. But why is that important to know? Huh.
The 256 minus 248 equal to 8 formula gets you the same number faster. But this is what it means. What that looks like laid out. Why 211 rounds down to 208? Subnets don't start wherever they feel like it. With a block size of 8, they start at 0, 8, 16, 24, and so on, counting by 8 forever. 192, 208, 216, 224. Your target has 211 in that octet. 211 is not on that list. It's not a place a subnet can begin. So it must be sitting inside a subnet that began earlier, and your job is to find which one. You round down, never up, because the subnet you're in started before you got there. 216 is a real boundary, but it's the start of the next subnet. Rounding up would put you in the wrong network entirely. 2 ways to do the arithmetic. Divide and drop the remainder. 211 equal to 26 remainder 3. Throw away the remainder. Keep 26 times 8 equal to 208. That remaining full, by the way, it means you're the third step into the block.
Okay. I need a second to process that. The target block down to a multiple of block size. Okay, I understand why this is 8. This is 8 because that's our last block. That's our last bit. Okay, maybe block's the correct terminology. But the target octet round down. We're okay, so the 211 is the original IP address. Man, dude, I really feel like we're doing magic right now. Okay. Some mental gymnastics for sure. 211, 208. Is a remainder of 3. Interesting. Try together block size here. Let's
Out by 8 until you'd overshoot. Tying it together. Block size and rounding are the same fact from 2 directions. The block size tells you how far apart the boundaries sit. Rounding down tells you which boundary you're standing behind. And once you have 208, the rest of the sheet falls out mechanically. Network is 208. The block runs 8 wide, so it ends at 215. Broadcast ease. The block runs easer. Next subnet is 215. Why didn't they need rounding? Because those octets were fully frozen. All 8 bits, so 135 and 87% stay exactly as given. Only the split octet ever gets rounded, and any octet after it goes to 0. That's why the sheet asks you to identify the interesting octet first.
Okay. I'm not gonna lie, these right here are definitely I thought I understood those, but very clearly I do not. So that's gonna require a little bit more understanding. When it comes to this, so we have one 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's why. Why did I do that backwards? That's why we have 11 host bits. So this is the part that I was having a hard time understanding, was the free addresses, because I know it's a huge number. But we should have, like, how did we have 2048 free addresses? I understand. Excuse me. I understand how we only have 46 that are usable because we minus 2. But how did we get that to 2048? Is it because we multiplied those two? Is it 255 multiplied by 7? That doesn't make any sense. That'd be such a huge number. Not huge enough. Okay. Let's hold on. I have the actual file. crap. Where'd it go? I think it's called study. IT certifications, packet tracers, Retroid Pocket 4. All right, here we go. I don't understand how we got the usable addresses. All I did was I took this image and I threw it in there. Okay, but the network makes sense. No, the network doesn't make sense. Wait. So this right here is the same as this. So somehow we're able to figure out the network from just the IP address from this 211. How?
Two separate steps, and the sheet compresses them, which is probably where it got lost. Step 1, where 2048 comes from. You have 11 free bits. Each free bit can be 0 or 1.
Yes.
Each one you add doubles the number of possible combinations.
Oh, crap. So you... no.
4, 3 bits, 8, 11 bits, 2048. That's 2 to the power of 11. Every distinct pattern those 11 bits can hold is one address. So the block contains 2048 addresses total.
Whoa. Say that again. Okay, that's 2 to the 11th power, which equals... Really? Okay, that is... yeah. So... every distinct pattern those 11 bits can hold is one address. So the block contains... oh, that's why it says this. 2 to the power of the host bits. It was right there. It was there the whole time. Okay, and then that tells us our thing. That means that what I did... oh, I already deleted it. That means what I did was wrong earlier. So then that's why this is important. We have to figure out the block size so we can figure out the target alt-tech round down. And that tells us what our network is based off of the interesting octet, which is the third one. And we know it's the third one because of this. Wow, man, it's all connected together. Holy shit. Okay, so then it goes back to, I don't understand how we did this. So it says down to a multiple of the block size. So... so then it goes back to this. Like, what? Like, how did we get that? Look at the third octet in the row and find the frozen last bit. Last bit that's frozen is 8. Okay, cool. So we have 8.
That last frozen bit is worth 8. It's the smallest amount the network part of that octet can change by. Flip it, and the octet jumps by 8. Anything smaller, 4, 2, 1, is host space. And changing those doesn't move you to a different subnet. It just...
what I don't understand, it says flip it and the octet jumps by 8. What does that mean? just moves you to a different address instead of that one. So block size equals the place value of the last frozen bit. Okay, that makes sense. I don't understand this part. So block size equals the place value of the last frozen bit. That's why /21 gives 8. Okay. The /21 of the example gives 8 because it freezes on 8 in the third octet. If it was /22, frozen one more bit, the last frozen would be 4. Okay, that's making sense. So if this would if this right here was 22, that would tell us to go to one more bit, which would be 4. Okay. The block would be 4 part. What I don't understand. So it said 256 minus 248. 4 gets you the same number. Well, where in the world do we get 248? The mask value in that octet. So you're saying the whole mask value is just this? So, let's test it. Yes. So the mask value is all of this added up. And then we subtracted the full value of the octet, which is 255. That's awful. Let me rewrite that. Hold on. I got a better idea. Let's do it this way. Okay. 255. Am I holding the stupid button? 248. I don't know why it's light all of a sudden. Okay. So then that's 15. That's 4. 15 minus 8 is not 8. It would have to be 256. Make this 16, which would make this 8. 0, 0. Interesting. Interesting. Okay. Let's trash it. Okay, things are starting to make sense. Now, I also have a subnet builder that's over here to help us build the subnet and get the wild card. Okay. We'll figure that one out in a little bit as well. Okay. But in the meantime, here's what we're going to do. Sure, you can view this. All right. Next problem. Actually, tell you the truth, I'd much rather it be this way. Can we do this? Okay. So let's do it. We have two, man, come on. Just reset this stupid tool. Reset tool. Okay. There we go. That's way better. Okay, we're good. Why is it? Whatever. I don't care. It's just a paintbrush. I just need it to do the thing. Okay, here we go. 203, 242, 142, 241, 25. Okay. So let's start adding this stuff up to figure out the bits. Now, we don't have to make this into binary. It does help, but it doesn't necessarily. What we really need is 25. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. Okay? Because we know that this is an octet, this is an octet, this is an octet. So this is 8 bits. I hate when it does that. This is 8 bits, 8 bits, 8 bits. So 8 times 3 is 24. And then this is going to be 1 bit. Okay? Which means that we're freezing it right here. This is where the line's going to be. So the network bits is going to be 25. Side R is 25. The interesting octet is the 4th, which we'll do that in a second, okay? We'll make the interesting one blue. So this is the interesting octet 4. The mask value, I'll worry about that in a second. Okay, let's go back. Okay, so it's 8. That looks like a stupid 0. It still looks like a 0. 8, 8, 8, 1, which equals 25, not 21. So then we got to convert that into the mask. So that's going to be 255, 255, 255. $128. Pretty sure that would be the mask. Which means that the wild card would be 255 minus 128, 127. 127. So that's the wild card. So the subnet would be this, what's up here. Okay. So then the mask value because we have to find its host, right? Okay. So the bits that are free, there are 7 bits free, which means we do 2 to the power of the amount of bits. So it'd be 2 to the power of 7, right? Because 2 to the power so then yeah. Yeah. It's 128. 128 minus 2, 126. Okay, but that still doesn't give us the host. In order to figure out the host, we have to figure out the block size. We have to figure out this stuff. So what's the mask value? So is the mask value what's frozen in that octet? 28 plus 64 plus 32 plus 16 plus 8? Yes. So this is what's frozen. This is the last block that's frozen. So then that means the value set is going to be 64 plus 32 plus 8 plus 4 plus 2 plus 1 is 111. The block size is 128. So then what would that be the target octet would round down to? Because 248 subtract by 208. Oh, it even says it. It's 256 subtract the mask. So 256 subtract. 145. So does that mean that the network, and we'll do this in, I don't know, orange. The network is network's gonna be 145, 142, 242, 203, 3. So then the first host would be 203, last host would be 203, broadcast would be 203, next that would be 203. All these would be the same. So the first host that would be usable would be 146, and the last host would be 254. The broadcast would be 255, and the next one okay. I don't know what the next subnet would be. Oh, no. The next subnet would be 3, 0. Okay. Whoa, what is... Whoa, that is literally never happened. That was... This is crazy. This is crazy. This is literally... Oh, that's why. It's because I have a monitor underneath my monitor right now. Okay, I didn't realize that. Okay, let's do this. Let's test our work. So the network address is 203.242.142.145. Damn it. 242, 142, 145. Well, damn. How'd I get that far off? That means literally everything's not going to be right. That means what I messed up with was this. Okay. Okay. I'm going to take a screenshot of this. We're going to ask our good friend Claude. Okay, where did I go wrong? Tell me, Claude. Damn. It has to do something with this. How did it get... Hey, what's up, dog? How did it get 208? Down to the multiple of the block size. Oh, the 208 is these things added together, I think. No, it's not. Because that would be 255. Is 208 this added together? Let's find out. Plus 64 plus 32 plus 16 plus 8. No, that's how we got this. This is what's frozen. This is what's left over. I don't know why we use 256 though. So then how in the world did we get 208? Because that's my problem. My target's not correct, which means that it fucked up everything. All right, Claude, talk to me.
Almost all of it is right. There's one slip, and it cascaded into 2 rows. The slip, target octet rounded down. Your block size is 128. So in the 4th octet, the only legal subnet starts are 0 and 128. That's it. The next one would be 256, which doesn't exist. Your target's 4th octet is 241. Round it down to a multiple of 128, not 128. Row U, row should the target. Row U, row should the target. Rounded, rounded, not 128 network. 200.
Now hold on, that doesn't make any sense to me. Because I got that 145 by adding up all those blocks. Because 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 is 127. That still doesn't make any sense. They got 128. Ah. So then where the hell did I get 145? Oh, because I subtracted? Why is it off of what, 256 and not 255? Is it everything off of 255? Okay, I'm getting closer.
Row U, row to the target. 42.25. 128. And broadcast 255. Those two facts pin the network down. 255 to 128 plus 1 equal to 128.
Right, so why did we add 1? Your block size was 120.
Hey, Watook brother, can you tell what is the purpose of subnet mask, please? My teacher can't tell me.
The purpose of a subnet mask? So, yeah, that's actually really easy. I can explain to you, like, literally like this. Okay. So, and I don't even need to use numbers to explain it to you either. Let's use a nice green, because green's my favorite color. Okay. So the purpose of a subnet mask is that we have IPv4. Okay. And we have 1, 2, 3, 4. We have 4 octets here. Okay. So originally IPv4 was broken up into different classes. A, B, dang it, dude. I hate when my fat fingers hit buttons. A, B, C, D, E. Okay. E is reserved, D is reserved for something. That was supposed to be for like corporate. This was supposed to be for like small business or something. And then this one was supposed to be for like public. Okay. But the difference is that each time you add an octet, you are making the possibilities of what's there smaller. So we have 255, 255, 255, and 255. And the reason it's 255 all around is that that's the maximum number that you could possibly have in this octet is 255. Okay, so the classes are really simple because A class started here, so it had the possibility to use this number and then any of these numbers. Then the B went here and C went here and D went here. Okay. That's why you see a lot of 192s. 192 is this block. So basically it's a matter of combinations of numbers and how many different combinations that there are. The different number of combinations that there are is the maximum amount of IP addresses for version 4 that we have. Okay. Now, what is hard about it is that the way it's set up, when you start dividing it up and kind of segregating, saying, okay, this amount's going to go here, this amount's going to go here, it starts doing it and doubling. That's why, like, when you make things go into binary, it goes 1, 2, 4, 8, 16, 32, 64, 128. Because it's talking about the bits, and it just doubles itself. Okay? So, what was happening is that when we divided things up into these classes like this, we were wasting not just thousands, but like millions of IP addresses. So, what we do is we start segregating them and cutting them in half. That's where we get like the /24 or /25, things like that. And what it does is it groups IP addresses and it divides them into different subsects, and saying this little section right here is only for the, I don't know, the principal's office, the marketing team, whatever you want to call it. And then this section's going to be over here. Subnetting basically takes a group of IP addresses and divides them pretty much equally into different sections. Okay. So if we look like here at the subnet builder that I have right here, we get these numbers based off of the amount of bits that are used in the octet. So the reason this is 8 is because the IP address for this is 255. If it's gonna write, is 255. The reason it's 255 is because we've added up all of these numbers. All of those numbers equal 255. So we're using all 8 blocks. So it gets an 8. It gets an 8 because it's the same. It gets a 5 because it's only using these. So this IP address is 255 plus 255 plus whatever 128. Here, I'll do it real fast. 128 plus 64 plus 32 plus 16 plus 8. 248. 248. This is 0. And then the 21. We got the 21 because we added up all of the blocks together. That's how we got the 21. This is your side R. I think I spelled that right correctly. Okay. And you, oh shit, it's right down here. So you can see this is down here. Okay. What this is saying is that the number of usable addresses because of this. Well, hold on. Don't worry about that. Okay. Because of this right here, the number of usable addresses is 2048. This is where we get into the problem of wasting a bunch of addresses. Because if I were to give this grouping to a marketing team of 5 people, that means only 5 devices, maybe 10. Let's just assume that there's every person has a computer, every person has a printer. That's 10 total devices that need IP addresses. But I, as the network administrator, gave them 2,448 IP addresses. I just lost a shit ton of IP addresses. So the reason we subnet is to break it up and only allocate out the number of IP addresses that we need to certain groups. It's for organizational purposes. It's to not overuse or over allocate IP addresses to certain people or to certain groups, or however it is that you divide up your program and things like that. Could you not use a subnet and just have the one thing? Yeah, absolutely you could. But then it gets really, really messy and not scalable. I'll give you one last example to send it home. Okay. If we, let's make this really big. Oh, crap. I need that not to be erased. Okay, good. Okay. Okay. If we, I wasn't expecting that at all. If we look at our, sorry, I'm not trying not to stall. Our home network. So let's say my home network is 192, I'm totally making these numbers up. 192.158.10.0. Okay? I get this from my ISP. Okay? And then I want to divide
hey,
this.
Not too long I watched your Net Plus videos and took the test, and boy, they were not similar questions, but I barely passed with 770. Thanks regardless, Red Heart.
Hey, nice. Nice. That's awesome, dude. What's your... That's crazy. They weren't similar questions. Because, like, I had the study material directly from CompTIA. Now, I will say that the practice tests that I took were vastly different. But anyway, back to my my original analogy, Jenny, is that I only have certain devices, right? So, like, let's say that this is my bedroom. Let's say that this is my office. Let's say this is my living room. Okay? I need to allocate enough addresses for all of these. Now, granted, this is a little bit of a bad scenario because I'm assuming that this is a public IP address when we're dealing with privates, okay? But the principle still stands. So that is why we subnet. We subnet in order to break apart things, to break apart the IP addresses, to allocate the correct amount to certain groupings, and for organization as well. Okay. VLANs and subnets are very similar, but they're not the same. I hope that helped. Let's read my friend Claude here. See what's going on with you. What's
Thanks, brother. I thinks is all about it. Subnet mask separates the network part from the host part.
Yeah, that's exactly right. Yes. What you need to understand is that and this took me a long time to understand, the network is its own IP address, and it's reserved for the network. And then you have your first host, your second host, your broadcast, and then the next subnet. But what I'm not understanding is, why are we using 256 and not 255? Where did this +1 come from? Bro, you got right is the 20.
Did you know that, brother, where I am from?
I have no idea where you're from. I mean, if you want to disclose that, you can. I would never disclose where someone lives on the internet unless you just tell me a country. I know that a bunch of people from India watch me. So the first octet you marked as 128, but the box row is the binary of the address itself, not the mask. 148 equals. So it needs 5 X's. What? What? Oh, I think it just clicked. Okay, hold on. Okay, yes, it just clicked. So the reason... Okay, we're going to do this in red. Okay, whoa. Oh my gosh, this is so much easier than I thought. Okay, the reason this is not 145, I don't even know where I got the 145. Like, forget that noise. So the 25 is all of these. That's what the point of these boxes are. Is that the X's, right? Because these are all the bits that are being used that are frozen up. The last one is 128.
Brother, I am from Pakistan and I really like your live class, but unfortunately not join the class, so it's my bad. Persevering face.
It's all fine, man. Yeah, and I just do this to help me study. You know, it's to help me stay accountable. So 128 is the last frozen block. So it's 128. So then it should be 256 subtract 128, 16, 4, that's 8, 4, 2, 128. Did I do that right? Am I having a stroke? No, that's correct. Okay, I think this one just so happened to be 128, so it all kind of worked out like that. So because 256 and 255 answers.
Can you tell me the one more question, please?
Yeah, sure. What's up, dog? Shoot. Because 256 and 255 answers 2 different questions, and this sheet uses how many values in an octet? 256. What is... But there's not... Oh. How many values fit in an octet? 256? Is it because it's adding 0? Is that what it is? The gap between those entirely because counting starts at 0. Yes, that's exactly what it is. Okay. I think I'm ready. I think we can do this. That means that our first host... 203, 242, 142, 146. Shit, I did it wrong. Can I go back? It's because I was going off of this. So that means our last one's going to be 242.142.255, right? 254. Oh, because it's reserved for the host. Or for the broadcast. 203, 242, 142, 250. Oh, shit. 242.142.255. Now, this is where I didn't understand because we're in the last octet. No, I do understand. So, it's going to be 203.242.143.
I don't understand about port security on a switch and how is it configured?
Ooh, that's a good question. That's a really good question. Oh, I got the last one right. Okay, cool. Let's ask Claude because I am also weak on that too. So let's do that. This will be the last thing that we do too. Okay, we'll do Anki flashcards later. Okay. Look. Okay. Stop. Stop.
Smiling face with halo.
Okay, hold on. I understand that now. Now, please help me with port. I do not understand. Explain it to me with a simple answer. Simple answer. Analogy. More in-depth answer. A real world example. Boom.
Brother, by the way, Claude, please you explain better than Claude and other AI.
Well, right, but I need to make sure that I'm going to explain it correctly. So I'll translate it in a way that'll make more sense to you, like whatever. But I don't want to give you false information. I want to make sure that I understand it, and that because I'm not super great with it either. So also, the answers you get out of AI depend on the prompts. If you're not giving good prompts, then you're going to get trash back. That's why I said give it to me as a simple answer, an analogy, a more in-depth answer, and then a real-world scenario. That's 4 different explanations of how something works. If you still don't understand after those, then like we got to do a different way. Like we got to work on how you're asking questions.
1. Simple answer. Port security locks a switch port to specific devices. You tell the switch only this MAC address, or only this many MAC addresses, is allowed to send traffic on this port. If something else shows up, the switch reacts. It either drops that device's frames, or shuts the port down entirely. It's a layer 2 access control that stops unauthorized devices from getting on the network just by plugging into a wall jack.
Okay. So it looks to me that it uses MAC addresses and determines how many MAC addresses are allowed through the particular port that you have designated. Let's see what the analogy is.
2. Analogy. Think of a reserved parking spot in a garage with an attendant watching her. The attendant writes down the license plate of the first car that parks there. From then on, only that plate is allowed in that spot. Someone else pulls in, and the attendant has three possible reactions depending on your instructions. Wave them off silently, turn the car away, say nothing to anyone. Wave them off and file a report, turn the car away, log it, notify management. Chain off the entire spot, nobody parks there again, not even the legitimate car, until you personally come and log it. Those three reactions are exactly the three violation modes, and the third one is the default. That surprises people. The default is the harshest option.
Okay, so to me, and this makes the most sense. This is what I thought it was. So you have a port on a wall. You can either systematically go in there and shut it down, or you can make it go up. Okay, those are the only two things you can do systematically. Okay, unless you put a security in there, which is kind of like an in-between, saying that this port will only recognize this, I don't know, controller, whatever it is, that gets plugged into this port. So like, this was in my classroom where my phone was a Cisco phone. It was plugged into the wall, and that jack only recognized that phone. I couldn't plug in my computer. I couldn't plug in anything else into that jack except for my Cisco phone. And my Cisco phone could only be plugged into that jack. I couldn't plug in my phone into anywhere else. So that one port knew the MAC address of my phone. It probably had some other internet phone things going on with it too. But that port knew that was my phone, and it wouldn't allow a computer or any other device to go in there. So it's not that the port was down, it's that the port was only allowing one device, or this very specific device. I bet you could probably use security port measures to make it so only printers with these MAC addresses can go into here, into this one spot. Let's see what kind of in-depth things it has to say for us.
In-depth. What the switch is actually tracking. Every frame arriving on a port carries a source and MAC address. The switch already learns these to build its MAC address table. Port security adds a rule layer on top, a maximum count of MACs allowed on that port, and optionally a list of which specific ones. How it learns the allowed MACs. 3 ways. Static. You type the MAC in by hand. Precise. But you're maintaining a list forever. Dynamic. The switch learns whatever connects, but forgets on reboot. Not much protection. Sticky. The switch learns automatically, then writes the MAC into the running config as if you typed it. This is what most people use. Plug in the right device once, save the config, and it's locked in. Violation modes. Mode drops traffic logs, a counterport goes down, protect these non-restrictees. ICs now shoot down ICCCCs. Shutdown is the default.
Okay, let's see here. So protect drops traffic. Yes, yes, yes. So then here's the difference between all the different modes. Wow, this is a really good chart. Okay, protect, restrict, and shut down. So it just automatically drops it, logs it. Protects means it's not going to log, but the restrict does. And then port goes down. Well, it's already disabled, so it's already down. Wow, so the port automatically just like dies if it is violated.
Enters air disabled state and stays there. It does not come back on its own unless you configure it to. Basic configuration. Interface gigabit Ethernet 0.
Oh wow, it even gave me this. That's pretty dope. So the interface is the G0/1 mode access port security maximum 1 MAC address sticky violation restriction. Wow. It's a lot more than I thought. Let's look at the real world example.
Gigabit Ethernet. 4. Real world example. A hotel style office with network jacks in the lobby. Anyone waiting for a meeting can plug in a laptop and land on the corporate VLAN. You want jacks that work for the assigned desk phone and PC, and nothing else. Desk with an IP phone and a PC daisy chain through it. The port sees 2 Macs, the phones and the PCs, so maximum 1 would break it immediately. Interface.
Wow, so even if you daisy chained it, so if you had it on if you had this on your port, you plugged in your phone, and then you daisy chained the PC into the phone, it would still shut down the port. That's wild.
Interface range gigabyte Ethernet. Maximum 3 gives the phone, the PC, and 1 spare. Restrict.
So the maximum is the amount of devices that are there. And then you'd manually put in, well, I guess you don't have to manually put in the MAC addresses. Wow, but if you have a bunch of stupid people, you could really be like have a bunch of like ports that are just always broken.
Rather than shut down, because a help desk ticket beats a dead port every time someone swaps a laptop. You get the syslog message and the counter without an outage. The failure mode this actually prevents. Someone brings in a cheap unmanaged switch from home to get extra ports at their desk. Restricts appear on a port rated for 3. With restrict, the extras get dropped and you get alerted.
This happened to a teacher in one of my schools. They bought like a little 4-port switch to like do whatever, and as soon as they plugged it in, they lost internet for their entire room. Well, through that port.
Without port security, that rogue switch quietly joins the network and you never know. One honest limitation: MAC addresses are trivially spoofed. Port security stops the casual and the accidental, the visitor plugging in, the unauthorized switch, the duplicate device. It does not stop someone who knows what they're doing and has read a legitimate MAC off a label. For real device authentication, you want 802.1 times.
So the real reason you do this, because it just said like, if someone knows what they're doing, they're gonna be able to get in. Kind of like a chain link fence. You have a chain link fence around your house, like people could jump over that, but it's still a deterrent, right? But the real issue is like someone plugging something in that's already compromised that they don't know. This happened to my girlfriend's school. The principal brought her home laptop, which was compromised. She didn't know it was compromised. Plugged it into the school's network and then accessed Teams, and then their entire stuff got hacked. So I understand. I hope that kind of explained that. That was very interesting. I knew that was a thing, but I've never really looked into it before. So I hope that helped. Now this, on the other hand, this still eludes me. There's got to be a faster way to do it. I think it has to do with I think everything is about the last block. The last block that's frozen. So this one's a bad example because it's literally 128. Okay, but now we're doing 24. So does that mean that my last block is going to be 1? My block size is 1. So I just want to be able to do this in my head. 157 plus 243 plus 247 plus 0. Because it counts 0. Okay, let's trash it. Alright. Let's try this one. I have a feeling it's going to be a lot easier. Okay. 157, 243, 247, 176, 24. So that means all of these are done. So this is 24. This is 24. That's 8. That's 8. That's 8. 0 equals 24. The mask is going to be not 225, 255. 255, 255, 255, 0, which means the wild card is going to be 255, 0, 0, 0. That looks like a 6. 0. So the no octet is split. Which octet is split? None. NA. The mask value in that octet. Okay. So let's, this 258, this 248 is these added. So what is it when it's like this now? So would it just be 255? And then 0? So then is the answer 255? Damn it. No. So it would be 1. Still having a hard time. Because this is 8. So then it should be 255, right?
Brother CA, you give me the some line or paragraph about how many usable host addresses are in A/26 subnet.
Some line or paragraph about how, yeah, yeah. Hold on. Yeah, I can do that. Let me finish this one and we'll do that one. So no octet was split. Okay, why thinks on that? $24. So then that means that the first host is gonna be 1. Yes, the last host is gonna be 254.
Buffering beaming face with smiling eyes.
Broadcast is gonna be 255. And the one after that is gonna be 157.243.247.1. No. 8? Yes. Okay. So you wanted one with 26, right? That's the cleanest case. It's actually the easiest one. Yeah, I figured as much. Okay. Well, I'll come back to that one. Let's do yours. 218, 145, 118, 118. And we have 26. So the stuff that's frozen, we'll do blue this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So the division is right here. So the bits that are frozen is 26. That's how we got the side R 26. So it's 8, 8, 8, 2 equals 26. Where'd my mouse? Man, I hate when mouse goes away. Like, why can't I wiggle my mouse and it go to, like, be bigger? You know what I'm saying? Okay. So that means that our net mask is going to be 255, 255, 255. No, not 225. Why do I always do that? Five, and then 128 plus 64 is 192. I think it's 192. Yes, yeah, it's 192. So the octet that's split is 4. The mask value in that octet. See, it's still these 3 questions that I still have a hard time understanding. So the mask value should be these things right here. Added up. 32 plus 16 plus 8 plus 4 plus 2 plus 1. 63. So the value should be 63. So that means 256 subtract 63 should be 190. 193. Is that correct? And then the target octet round down. Down to the multiple of the block size. See, I just don't know how I got 208. I know it's explained to me a bunch of times. What was your original question? How many usable addresses? So to answer that question, we can go back here. We don't need this in order to answer that. All we do is we take our host, which is our frozen, okay, which is 26. So we do 2 to the power of 26. I hate that that has that button. Okay, 26. So 2 to the power of 26. So that'd be no, I did that backwards. It's 2 to the power of the host. I did the frozen. 1, 2, 3, 4, 5, 6 to the power of 6. 64. So that's how many usable free addresses you have. Well, no, it's actually 62 because you have to reserve the host. But finding the network, man, that's the hard one. Like, I don't understand. So then the network's gotta be... I feel like I did it. Just show it to me. Okay, so it's 64. I got close, I think.
Thanks _ by the way, where you from, brother?
I'm in Texas. Good old Texas. Lone Star State. Everything's bigger. Let's see here. I still do not understand the crap. What's it called? Target octet round down. Okay, this will probably be the last one for real this time. Yeah, shoot, it's almost 11. I was supposed to call my dad at 10. He probably texted me. The reason it isn't clicking here is that your block size is wrong and round down is impossible without the right block size. Let me fix that first. How's my block size wrong? The block size should be that, right? It should be 256 minus 63. Your A plus A is right. 2 mask bits in the 4th octet. Those 2 bits are 128 and the 64. You wrote 63. Yeah, how did I get 63? No, I got 63 because I added that hoe together. I bet it was my dad. No, it wasn't. 32 plus 16 plus 8 plus 4 plus 2 plus... Oh, God damn it. Okay, 32 plus 16 plus 8 plus 4 plus 2 plus 1. Oh, plus the 0, right? Okay.
Houston maybe.
I'm in the coast, but yeah, I'm in Texas. I lost my train of thought. I'm so sorry. Okay. I put 63 because 32 plus 16 plus 8 plus 4 plus 2 plus 1 is equals 63. But I didn't factor in that we count 0. I think that is where I went wrong, question mark. Okay, see here. C3 is usually your wild card. So that number is real, just in the wrong box. Your mask row already says
keep going, flexed biceps.
thanks, dog. Which is correct. So you had 192 on hand.
Person turquoise waving, person turquoise waving, person turquoise waving.
I guess my restream does not handle that emoji. Okay, so I did have the 192. How did I get 192?
Beaming face with smiling eyes, brother. I think you need some rest.
Yeah, but I'm gonna figure this one thing out first, and then I gotta go. I have to fix a lawnmower after this. No, this is correct. Yeah, 190, 192. Because 128 plus 64 is 192. So this is the mask because of these things right over here. So then the other side should have been 63 because plus 63 equals 255, but not 256 because we count 0. Okay. Count up to your block size. You'd pass the strength, divide. Where'd you get 118 from? Oh. Divide 118 by 6. Okay.
You wrote 63 for the mask value, and 193 for the block size. The 63 is actually your wildcard octet. 255 minus 192 equal to 63, so that number is real, just in the wrong box.
Okay.
And the row already says 255.255.255.192, which is correct. So you had 192 in hand. It just didn't make it into the middle column. Block size equal to 64. Now the rounding. Block size 64 means subnets in the fourth octet can only begin at multiples of 64. The mechanical way to do it.
Count up by your block size until you'd pass the target, then stop at the last one. 0, 64, 228, too far. That's past 118. Back up 164. Or divide, which would go to 1. Remainder 54. Keep the whole number, drop the remainder. Always down, never up. Is a real boundary, but it's the start of the next subnet. Round up would put in a network address. The round down value is the network's interesting octet. Rule is octets before the interesting one, copy them unchanged. The interesting octet, your round down number, 64. Right, but this didn't explain to me how we got 118. No. Okay, so we started with 118. $64. So is 64 32 plus 16 plus 8 plus 2 plus 1 I missed something. Yeah, I did. I missed 4. So is the block size... No. Is the mask value in the interesting octet, is it always the host? Is the block size that is in the interesting octet always the host? When is always the network? I think it is. I need a shave. Because if that's the case, okay, so then the host, the first host is going to be 65. The last one is going to be 254. Oh. Why? Because we only have 64 usable addresses. So we can only add 64 to the host. Or to the first one. So if we subtract this, let's see what we get. $61, because 61 minus 2 would be 63. What gets me is that sometimes we count 0 and sometimes we don't.
Good instinct to go back and check, but the diagnosis isn't quite right, and the actual reason is more useful to know. What actually happened with the 63? 32 plus 16 plus 8 plus 4 plus 2 plus 1 equal to 63 is correct arithmetic. The problem is, which bits you added? Those 6 are your free bits, the host side. The mask value is the sum of the frozen bits, and in the 4th octet that's only 128 plus 64.
What?
Okay brother, I do my some clients projects about digital marketing, so tomorrow I will come. Have a nice day. Hugging face.
Nice, man. Good luck with that digital marketing stuff. It's super fun. I used to do that stuff too. The host side, the mask value is the sum of the frozen bits. And the 4th octet, that's only 2. Okay, hold on. I'm going to test this theory here. So, 8 plus 4 plus 2 plus 1 plus 1. So is the host. No. Okay. I need to take a break. Yeah. It's not clicking. So, we'll do the Anki flashcards like another time. A lot of people really don't like when I do the Anki flashcards, but they help me out a lot. So we'll come back. We'll keep practicing the subnetting and stuff and doing all that good stuff. The next stream is going to be next Wednesday, this coming Wednesday, at 8 a.m. I don't know if we'll go until 11 or not. Maybe we will. We'll definitely go through the Jeremy stuff. We'll do the packet tracer, and maybe we'll do some more subnetting, some things like that. So that's what's going on. If you like the gaming stuff, tomorrow we're going to be playing the new Halo. So if that's something that interests you, come check it out. If not, that's fine. Other than that, like, follow, subscribe, share, do all the good stuff. Appreciate all the love and support. I really like that we're all like supportive of each other, and like we're all just trying to learn and stuff like that. I really like that. Thank you guys for always being that way. Other than that, that's where we are. That's what we're doing. I will catch you next Wednesday at 8 a.m. This coming Wednesday at 8 a.m. Hey, and remember, work with what you got and build what you need. I'm out, guys.